Welcome to my presentation once more on my dissertation, which is entitled Experimental Evidence on the Adoption of Innovations and Robotics for Sustainable Crop Production. And since I would like to give a very broad overview, I have reduced the amount of slides a little bit to present only those which are very important for PhenoRob from the experimental and the smart farming background. So let's jump right in. You're all aware of the challenges for global agricultural systems. You know that global population is projected to increase to more than 10 billion people by the end or in the second half of this century. And along with that, food demand globally is also expected to increase. And depending on the scenario that you're looking at, you might end up in 2050 with an increased food demand by more than 35 to 56 additional % compared to today. And meanwhile, agricultural systems are intensifying as well. And what you are looking at right now is the intensity at which pesticides, that includes fungicides, herbicides, and so on, are used not only absolutely, but as the intensity. So the use of pesticides in kilograms per hectare. And you see, while the Americas, that is North and South America, definitely lead the chart here, you see that in all regions across the globe, the intensity that pesticides are used has been rising over the last couple of decades. Furthermore, biodiversity and the biomass of insects is decreasing as well, or is in threat. So here you see a study from Hallmann and colleagues who looked at the development of biomass in protected areas in Germany over more than 27 years. And what they found is that these protected areas, which were adjacent to agricultural systems, showed a decline of biomass of insects by 75%. And one of the reasons that the authors state for this decline was actually said to be intense agricultural systems. And that's another example for the use and the decrease, in fact, or the loss of agricultural area from Germany, so one of the developed countries. Let me quickly pull out my laser pointer. So yeah, highly productive countries such as Germany. And what you see here is that the potential area which can be used for agricultural purposes is decreasing, although these numbers are all positive. And if you see here the use, you see that in the last year that this data was recorded, in some 58 square kilometers were used. Sorry, hectares. That is, hectares were used. Were reused for housing and industry purposes, for leisure, or for traffic, so infrastructural purposes. And if you convert that to a number which is more intuitive, you can see that 81 football fields per day are lost for these usage purposes. So this is land which cannot be used for agricultural purposes. So if you put all these things together, if you puzzle the pieces together, you find that business as usual, if you want to meet the challenges that we talked about, such as global food demand increase and the population decrease and biodiversity decline, you come to the conclusion that business as usual cannot be the path towards the future. But what we actually need to meet production and biodiversity needs and save the environment is a way which is called sustainable intensification. Basically producing more and saving the environment while becoming more efficient regarding inputs. And sustainable intensification needs to be understood as a toolbox with very context-specific measures. In our cluster, PhenoRob, we think, and we continue to think, hopefully we go into the second period, that smart farming technologies equipped with high precision sensors and highly precise tools can be one remedy towards sustainable intensification. And what we're talking about here is mechanical or chemical weeding with highly precise application, the inspection of the nutritional status of plants in the field with hyperspectral camera imaging, or drone-based pest scouting. And all these pictures are actually taken within our cluster. So the overall research question of my thesis, therefore, was, from an economic perspective, what determines the uptake of sustainable agricultural innovations, in particular smart farming technologies, with a focus on the farm level. So like I said, the farmer on farm level is in the focus. And my thesis is structured in the following way. The first chapter is a meta-analysis in which we compiled quite a few papers on agricultural adoption across the globe. And then chapters 3, 4, and 5 are experimental chapters which build on each other. And like I said, I would like to only lose a few words on the meta-analysis while focusing on the experimental chapters in this particular presentation today. So the meta-analysis, like I said, had the motivation that there's a lot of literature on the adoption of innovations in general, not just smart farming technologies across the globe, but because they are very context specific, most of them, if you put them together, there is no conclusive answer to the question what determines adoption. And therefore, the objective for this chapter was to compile all these adoption studies and identify very clear determinants that can be used for future research. And what we found is that most of the determinants that are actually included in research turned out to be insignificant when you looked at them across the study level, on the meta level. And because most people think that economic variables may be very important determinants, we looked at those particularly, but what we found is that most of them turned out to be insignificant across the board. But another interesting thing is when we found that there were variables significant, they were not from the economic field, but they were from the behavioral or from the institutional or even from biophysical variable groups. And I will go into that a little bit more in later slides. And what we also found that when we disaggregated our large sample of more than 530 studies that were in our data set, we could not find that the results changed in any direction. And therefore, we thought that we should do more precise research and go into the study level, into the experimental field. And that's the focus of chapter 3. Like I said, the motivation in the beginning was that we know the potential of smart farming technologies. We know their environmental potential particularly, but we also know that farmers are hesitant, or their determinants or their perceptions of smart farming technologies are under-researched. So the objective of chapter 3 is to investigate the attitudes of farmers. Like I said, the behavioral variables in the meta-analysis were under-researched, so this chapter answers to that, and we dig into the attitudes of farmers towards smart farming technology adoption. And furthermore, we test particular hypothetical policy scenarios in their effect to positively drive adoption. And the methodology was here an incentivized lab in the field experiment, and we analyzed that with a statistical approach. And our sample was based on 334 actual crop farmers. And the experimental design for the study looked like the following. We conducted a business simulation game. So basically, the farmers who participated in this online survey were told they have 50 hectares of hypothetical farmland on which they should use 3 weeding technologies to conduct their weed management. In particular, those were the broadcast application, which is the conventional status quo, spot spraying, which is a tractor with a basically with a spraying boom for herbicides, but the driver was still a human driver. And the new technology was the weeding robot, so a fully autonomous application of herbicides on the field. And we told them that while broadcast application, like I said, was the conventional status quo, it would have no positive effect on the environment, but it would be very beneficial for the private profit. And spot spraying as the intermediate technology and the weeding robot as the fully smart technology were said to be somewhat less profitable because they were new and expensive technologies and prone to error in the field. But because they could save substantial amounts of herbicides, they were told to be beneficial for the environment. So with that choice between these 3 technologies, we wanted to see whether farmers are willing to forego a certain amount of their profit, of their private profit, for the benefit of the environment. So we wanted to test this trade-off here. And we played 2 rounds. In the first round, we played just the baseline. So we observed all participants, how they distribute their fields to these 3 individual technologies. And then in the second round, we randomized the sample in 4 groups and assigned them different policy scenarios. The first group was the control group, which is very important in experimental settings here. The second group was a subsidy group. So we said each farmer who would use some smart farming technologies would receive an economic incentive, a subsidy for using new technologies. The third group was the nudge group. So basically, this was framed like a legislative text which would appreciate the benefits and the daily work of farmers, how they protect the environment and how they guarantee and steward safe production of viable food every day. So they would basically receive an honorable text. And the fourth group was the combination of the financial incentive, the subsidy, and the nudge text. And then we had them play the same game again. So first of all, I show you the results of the baseline analysis. And what you see here is that farmers who indicated they had higher levels of very pro-environmental attitude showed that they wanted to use more weeding robot and they wanted to use less broadcast application. So here, higher levels of pro-environmental attitude are clearly associated with higher levels of smart farming technologies, the weeding robot in particular. And also farmers who said that they were very interested in new technologies and that they would inform themselves individually about new technologies in their daily work showed that they would like to use more spot spraying compared to reduction of the use of broadcast application. However, we found that whether they are afraid of their data being lost by the use of smart farming technologies, for example, through sharing with cloud services or through sharing with large companies, had no significant effect on their weeding technology allocation whatsoever. And then in the second round, we tested the policy scenarios, T1, T2, and T3, all those scenarios relative to the control group, like I showed you. And since you see here that the confidence intervals, all of them include the 0, none of the policy treatments had any significant effect on weeding higher levels of smart farming technology adoption. And that was a little bit disappointing. So we went back into the data to find the causes for that. And what we found is that here, from the baseline towards the treatment round, all groups change their behavior towards smart farming technologies in comparable patterns. And you may say this is what you want to see, but the problem here is that the control group here, which did not receive any treatment or any incentive to go towards more smart farming from round 1 to round 2, behaved in the same way. Or in other words, just by having them play another round, increased their willingness to use smart farming technologies. And this is something odd because you don't want to see that in non-treated experimental groups. So we pooled the data. So that is, we put all observations from the first and the second round together and clustered them by the farmer ID and included a dummy which controlled for round 1 or round 2. And what we found is basically statistical evidence for what we saw in the descriptive statistics one slide before. Having farmers play a second round is statistically significantly and quite strongly associated with higher levels of smart farming technology adoption and lower levels of broadcast application, rendering all treatments effects statistically insignificant. Yeah, that's basically what I said. So we saw that farmers on average are willing to use smart farming technologies. We saw that they moved towards smart farming technologies. And we saw that attitudes, particularly pro-environmental attitude and personal innovativeness, matter a lot for these numbers. However, the policy scenarios were statistically insignificant. And although they showed a somewhat positive effect, so they were numerically pointing towards the right direction, they turned not out statistically significant the way we wanted. And we identified an experimental phenomenon which definitely requires a further look. And therefore, we dedicated chapter 4 to digging deeper into that. Yes, so the motivation, like I said, for chapter 4 was the round effect. And therefore, chapter 4 is to be thought of as a methodological amendment to chapter 3. And the objective was to find out whether this round effect that we identified in chapter 3 is specific to farmers, or, and that's called a subject pool effect, or whether it is in fact a methodological issue which can be found in many multi-period business simulation games. So we played the same game again, a lab in the field experiment with a fractional multinomial logit regression model, But this time we didn't use farmers, but we used students, which we recruited from agricultural research institutions across Germany. We had them play the same game again, 50 hectares, 3 weeding technologies, which differed in their environmental and their economic impacts. And for the purpose of this study, we reduced the complexity with the treatments a little bit, because after the baseline, in which all students played the same game, we only had them play one scenario which reflected the subsidy compared to the baseline. So we wanted to simplify the game, basically. And what we found here is very interesting. Compared to the farmer sample, the behavioral determinants, personal innovativeness, and the degree to which students are afraid of their data being lost by the use of smart farming technologies had the complete opposite direction. So higher levels of innovativeness and higher degrees of trust in the security and privacy of the data were associated with higher broadcast application, so higher levels of conventional technology use and lower levels of smart farming technology use. And in the second round, where we looked at the subsidy, we saw that the subsidy had, in fact, a very significant effect on spot spraying use, and the effect was negative and highly statistically significant for the use of broadcast application. So the subsidy worked, in other words, while in the farmer sample it did not work. And when we did the robustness check again, the full cross-section analysis, we found that having them play another round was not statistically significantly associated with anything. So the results remained robust. So what we can find here is that we could not reproduce the round effect with students. And therefore, we think that we had found evidence for subject pool effects, or in other words, farmers show the round effect and students do not. And this is clearly a gap in agricultural economics literature, because first of all, it shows the relevance of a control group, because we hadn't found this effect in the first experiment without a control group. And this would have left us with a highly significant treatment effect. And this would, if you use that for policy information or for the information of future experiments, would lead to highly inefficient and very costly policies and experiments. And therefore, we think this knowledge is highly relevant, not only for agricultural economists, but also for policymakers and advisors who want to use results from such experiments for future policy design. Now let's come to the last chapter. And this is the analysis of smart farming technology adoption through a purely behavioral lens. Because like I said in the beginning, mostly economic variables are used to analyze what drives adoption of innovations in general, and behavioral variables are largely, let's say, they are imbalanced compared to economic or, let's say, profit maximizing approaches. And therefore, the objective of the last paper, which came out in Journal of Environmental Management in the beginning of this year, was to apply a psychological theory to this smart farming context, and not only apply it, but in fact extend it to see if we can improve the model fit with our behavioral extensions. In particular, we used the theory of planned behavior and analyzed it with partially square structural equation modeling. And we based that on a subset of the farmer sample that we collected for experiment in chapter 3. And the structural model in its baseline looks like the following. You want to find out what drives the intention, so the ex ante adoption willingness, so to say, of a technology or of a behavior. In our case, this would be spot spraying. And you hypothesize that farmers' attitudes towards the intention plays a role. You hypothesize that the subjective or the social impacts of their professional or their family environment play a role, and you hypothesize that the degree to which farmers feel that they are capable of doing the task and that they are financially and technologically equipped to do the task play a role. Furthermore, we read a lot of literature to extend this model here in blue, and we said that pro-environmental attitudes may benefit the attitude towards the technology itself. And we said that the degree of personal innovativeness may drive the attitude towards the technology itself. And we said that beyond subjective impacts, we also said that farmers' personal moral compass, so to say, the degree to which they think they should care for the environment and reduce the amount of herbicides used, play a role. And I will spare you with the details of the results, but the main message from our analysis is that we could confirm the baseline theory in the context of spot spraying adoption. And the results for the extended model were somewhat mixed. In other words, while we found that pro-environmental attitude did not play any role for the attitude towards the technology, that is spot spraying itself, but we found that higher levels of personal innovativeness did in fact drive higher levels of the attitude towards spot spraying. And something that is very important for future research and especially the design of policies, moral norms. Like I said, the degree to which farmers think they should reduce herbicides applied on their field had a very significant total effect on the intention to use spot spraying through the effect on the attitude towards spot spraying. And comparing model fit measures here for the baseline model and the extended model shows us that we could slightly increase model fit from the baseline to the extended model, and that renders our extensions, let's say, theoretically and experimentally relevant for the future. So, very short, we could confirm the baseline theoretical model and could somewhat confirm that some model extensions were helpful to improve model fit. And again, this analysis shows us the relevance of behavioral measures, for example, the attitude and moral norms for the adoption intention of spot spraying in our case, but smart farming technologies in the broader context. So taking all these chapters, and some of these turned out into papers together to come to our contribution of this dissertation, we can say that chapter 2 is the largest, to the best of our knowledge, the largest and most updated available global database of adoption literature in the agricultural context. Chapter 3 is the first conceptualization of smart farming technologies in an experimental or behavioral experimental setting, and we associate particular attitudes of farmers with particular attributes of technologies themselves. And therefore, because this was not a real experiment, this may enable very cost-efficient policy evaluation before they are rolled out. Because if you think about the subsidy, if you pay out a subsidy to many farmers thinking it might be effective, but it turns out to be ineffective, you lose a lot of governmental and that is taxpayers' money, and you want to avoid that. Chapter 4 is the investigation of an under-researched phenomenon in agricultural economics research, and this allows us to formulate recommendations for future experimental designs. And lastly, like I said, chapter 5 is the first extension of the theory of plant behavior in the smart farming technology context, and renders some interesting insights for future experimental designs. But of course, my dissertation has limitations, and therefore I would like to point out some future research directions. First of all, chapter 2, the meta-analysis, has a very coarse perspective. So we look at many innovations and contexts at the same time, and therefore it is difficult, in fact impossible, to derive direct policy implications. However, the database is huge and is definitely suited for future analyses, and we would like to highlight this extent of the database and make it available for future research. Chapter 3 is highly assumption-based because smart farming technologies are still in their maturation phase, and as more technology attributes reveal and actually roll out on ground, we may be able to conduct experiments with more realistic technological attributes, and this is still to come. Chapter 3 and Chapter 5 have a low degree of external validity. So because we used a hypothetical setting and very controlled experimental conditions, the analysis left the farmers, or the experiment left the farmers very little room for improvisation as they would do in their daily work on their farm. Furthermore, we definitely used a convenience sample. So that is, farmers who participated selected themselves into participating in the survey. That's called self-selection bias. So we could not have a representative sample, and therefore we may have observed early adopters. So those people who are very interested in technologies and may not be representative of the underlying population of farmers. But again, we think that it is those farmers, those early adopters, who drive the innovation and who kickstart, who initiate the innovation, and may therefore nonetheless be highly interesting as research objectives, as research subjects in this particular context. And another aspect is that adoption is not a binary choice. So neither do you choose to stay away or to adopt the technology, but you choose to look at it, maybe try it on a percentage of your field, and then increase the use of that technology. So clearly it is more complex than our binary decision model here in this context. And we think that in the future, adoption should be modeled as a process, first of all, and not only on farm level, but on the regional level. And some of my colleagues in the CP6 of PhenoRob have done so. So I'd like to highlight that their contributions to parameterizing group effects and also regional level effects are very important in this context again. Okay, this will be my last slide. Of course, I have to formulate policy implications since I am an agriculture economist. And in the short term, I recommend that there is no, or I would say that there is no one-size-fits-all strategy, but we need contextual alignment. Like I said, we need to look into regional context and identify dynamics of adoption, and then support them with very specific policy approaches, of which some should be based on more communication, collaboration, and the exchange of know-how. So opportunities for farmers to interact and exchange the knowledge regarding smart farming technologies. But they should also be combined with financial incentives, and not only, let's say, subliminal incentives, but substantial incentives to really kickstart the innovation and to show farmers that there is a public appreciation of their work that really not only compensates, but overshoots the losses that they might accrue or might incur when moving to smart farming technologies. In the long term, or medium to long term, I think, and this is definitely not in the scope of this dissertation, is that we should rethink farming with the burgeoning amount of smart farming technologies that come out. Because a farmer is now, let's say, an agronomist trying to optimize the profit of his farm or her farm. But in the future, as technologies become more autonomous and digitized, the same happens with the business themselves. And therefore, we should, as a society or as a state, provide learning opportunities to acquire digital skills and enable farmers to keep up with this development and not be substituted by increasingly autonomous technologies. And therefore, we need an ethical and also a legislative action plan to embody or to accommodate artificial intelligence and big data in farming in general. And that's it. Thank you very much for your interest, your attention, and I'm really happy to answer your questions.